here. And today I'm going to share with you some work which is mainly around dual unitary circuits, but I hope to touch on some of the quantum information aspects of this. And so this has had a lot of collaborators on the way, but the main collaborators in this is my PhD student here who's finishing up, Suhail, and my former postdoc, Arvinda. So the motivations are to find simple, in some sense, solvable models of many-body quantum chaos. For those of you familiar with classical dynamics, which I assume all of us are, we have some of the most simplest maps, such as the Baker's map or the cat map, which are in some sense solvable, although they are really highly chaotic systems. So can we have these kind of equivalent quantum many-body systems? And a secondary motivation is to also look at the ergodic hierarchy, which is a hierarchy of increasingly complex systems, starting from ergodic systems up to mixing, and then Kolmogorov, and then Bernoulli. So this inclusion sign means that every mixing system is ergodic, but not necessarily Kolmogorov. Every Kolmogorov system is necessarily ergodic and mixing. And at the apex of the hierarchy are Bernoulli systems, which are guaranteed to be ergodic, mixing, and Kolmogorov. Ergodic we understand as, in some sense, a space average equals a time average colloquially. Mixing means that correlation functions decay. Kolmogorov means they actually decay exponentially, and there is a positive Lyapunov exponent. And Bernoulli, at the apex of it, are kind of strange systems which have no memory at all in time, and the correlation functions instantly decay. In a sense, they are as random as they can be, and they are equivalent, strictly speaking, to purely random processes such as a coin toss. So is there a quantum hierarchy? For a while now, I mean, this is, of course, related to the questions of quantum chaos. And if so, what are the candidates for a Bernoulli system? So I wish to talk about one possible candidate which satisfies at least some of the properties of classical systems, which are Bernoulli. And I hope to emphasize the interplay of quantum information and quantum dynamical systems. So as the models are really built on unitary circuits, and random unitary circuits are being studied now very prominently. They are as models of non-integrable quantum many-body systems. They provide unitary K designs. That is, they are really as if we are sampling these unitaries from a hard measure to some extent. And so they are very random. And they are also natural to implement in today's era, where you have quantum computers and gates that are available for us in at least going up to 100 qubits or so. So it's natural to implement that. And for example, this paper, which claimed that there was quantum supremacy and has been examined closely since its publication, is essentially a random circuit, a random unitary circuit. And what was examined was the distribution of the state at the end of several time evolutions of in a way, random Floquet system. But what I want to talk about is not really random circuits, in the sense that the elements are kind of special elements, although we will introduce some kind of randomness as well. And this speciality is the so-called dual unitary, which has already been discussed in one of the talks earlier in this conference. And I think this paper was essentially the first one which at least defined the notion of dual unitaries, this paper of Bertini, Koch, and Prosen, where they calculated exact correlation functions for dual unitary lattice models in 1+1 dimension. But actually, its roots go back to at least these two works in 2016 by Gutkin, Osipov, and the Thomas Gore group. I think I need to go back. Yeah. So, but there has been a real explosion of works on dual unitary circuits from many possible approaches, from entanglement to measurement-based phase transitions and so on. So it's a very large literature. I've just put down here some of the early works which laid out the basics of dual unitary circuit. So what does dual unitary mean? Well, first of all, unitary. And what we have in mind are really two particle operators which together build a circuit. So let's consider bipartite. So each of these systems is of local dimension q. And so we have a unitary operator in dimension q squared. And the local basis is denoted as I alpha. And then here is a unitary operator whose input is j beta. And this is the unitary operator. Its output is I alpha. So it's a tensor network kind of, or a graph picture of this unitary operator. And let's say that the adjoint is of a similar kind, but with a red color. Then for just the unitarity that you adjoint as identity would be represented by this contraction of these two legs. So we have U adjoint first, there's an input of J beta, and then this contraction takes care of this multiplication, and then this I alpha, but that produces just this identity matrix here. And of course, this other order is also true. You can put the red one on top. Now, we can construct then circuits by going further and putting many of these unitary operators in a line. Here, for example, I've put 4 of them. Since they are bipartite, it refers to an 8-particle unitary. But at this point, only the neighboring sites are interacting. So in the next layer, the next neighbor, 2 and 3 are interacting and so forth. So between these two layers, every particle is interacting with its nearest neighbor, and therefore this is forming what could be a globally entangling operation. So this actually refers to one time step in a dual unitary circuit, and a Floquet circuit would just repeat this t number of times. So here, for example, I've just written this particular circuit in terms of the fundamental unitary operators. So for the purposes of this talk, in fact, all these unitary operators will be identical. And so there is translational symmetry. And in fact, you can write then this dynamics on 2 power L particles as the script u to the power of t, where the script u is this particular thing, set of unitaries, which is u tensor L, and then it just the same thing translated by one side, t being the translation operator. Now, there is the, if one wants to calculate some quantities like the trace of the propagator, trace of u, which is the many body u to the power of time t, then we basically have to calculate some diagrams such as this, where there are t layers in the vertical direction, and there are 2L sides in the, actually there will be 2t if you include every layer, and 2L particles along the horizontal direction. Now we apply periodic boundary conditions both in space and in time because of the trace, then it's easy to see that the same operation can be viewed alternatively, as instead of looking at it as if time is going from here up, we could think of this direction as being time and this direction as being space. And therefore, the same quantity can also be written as a trace of a tilde many-body operator to the power of L, where L is the number of particles in this. So a 2L particle propagator, which is constructed out of this two-body operator U for a time t, is exactly equal to a 2t particle propagator with a propagator U tilde over a time L. So these are these are single time propagators. Actually, they should be really script U. Now, what is it which constructs U tilde? And U tilde need not be unitary in general. So what actually constructs this U tilde is, you can see from these pictures, is basically something where we are thinking about the vertical as space and the horizontal as time. So there is a space-time interchange which is happening here. And therefore, that is, you're taking this gate and you're viewing this axis as actually now space, so that is ij, and alpha beta as the outputs now, and the input is ij. So this is the U tilde operators that are constructed out of this operator UR2. This is actually a realignment operation in quantum information theory, and basically it's got by just interchanging these two indices here. So it's a permutation of the original unitary matrix, as you can see here, where alpha and j are kept fixed and I and beta are being interchanged. So this is a realignment operation. And as far as unitary matrix is concerned, it's just a reshuffling of these. And there is a simple identity which you can work out for local operators under realignment becomes a projector of this form. This is rather useful. And what happens to, what exactly are dual unitaries? I wish to give you some idea of that. So if U is dual unitary, then this is something where the space-time dual circuit is also unitary. In that case, this realignment UR2 is also unitary. So then it's called a dual unitary operator. So U is just a bipartite unitary operator. It's considered to be dual unitary if its realignment is also unitary. So in pictures, there is yet another contraction which results in identity rather than the first contraction which I showed you, including the first contraction which I showed. So there are two views. One is a dual unitary operators have maximum operator entanglement. So this is easy to see. We expand the unitary operator in terms of its Schmidt decomposition, and then you can use that identity which I just showed you in the previous slide and write this UR2 adjoint, and then you will see that what you have is really a spectral decomposition. So if this itself is identity, then this spectra lambda I is flat. All of these lambda I are equal to 1, and therefore this is a maximally entangled unitary operator. And these, for example, you can measure the entanglement by linear entropy. Then this is the operator entanglement, and it reaches a maximum of 1 minus 1 over q squared, which is the case for all dual unitary operators. So they have maximum operator entanglement. And they have, for example, the swap operator, which just interchanges any two subsystems, is an example of that. And operators which reach the minimum operator entanglement are, of course, just unentangled operators, including the identity, for example. But there is another quantity, which is the entangling power, which is defined in the following way, that we take some product states, operate a bipartite unitary on that, and then find its entanglement, say its linear entropy of the subsystem, and then average it over all product states. So this is called the entangling power of these unitaries. And it turns out that there's a very nice equation for this in terms of operator entanglement, as I introduced before. It involves operator entanglement of U, but also the operator entanglement of U times the swap operator. So in particular, if EU is equal to ES, which is the case for dual unitaries, it's maximum possible, the entangling power of dual unitaries is given by this. In particular, the entangling power of dual unitaries is not the maximum possible. For instance, the swap operator has 0 entangling power. That's also clear. It's not entangling anything at all. So what are the operators which maximize entangling power? They are both dual unitary and T-dual unitary operators, where T-dual unitary operators are unitary also under partial transpose. Partial transpose is something which is more familiar to us from the Perez partial transpose criterion, where you just interchange one of the subsystems, any one of the subsystems. So This also has to be a maximum. In that case, then the partial transpose is also unitary. Uh, so in so so the entangling power is 1 if and only if this bipartite unitary is itself unitary, of course, and then its realignment and partial transpose are all unitary. This has been referred to in the literature variously, but at least in two different ways, as a perfect tensor and as a two unitary. And there's a fact from quantum information theory that there are no perfect tensors or two unitaries for qubits. They don't exist. You can see here, this is the plot of entangling power versus gate typicality, which is defined like this. And you can see that entangling power does not reach the value 1. The C0 gate reaches a value of 2 by 3. Whereas you can go to Q trits, Q equals 3 local things, and you can achieve an entangling power of 1. So there is a very crucial difference between qubits and Q trits. For qubits, there is in fact a parameterization of all dual unitary operators, which is essentially a 13-parameter family. But apart from these local unitaries, there is only one non-local parameter J, which is constructing all dual unitaries. And there are, as I said, no two unitaries in the case of qubits. There are many ways of constructing, although it's not very clear how to construct, for example, dual unitary operators even in Q equals 3 or in general. Only for qubits it's known. But there are many ways. I will skip the details. It's based on block diagonal operators, permutations due to orthogonal Latin squares, cat maps, Fourier transforms. And finally, there is a numerically robust method of creating ensembles of dual unitary and maximally entangling operators. You can see this paper of ours for more details. I think I'll skip these for more details. And also dual unitaries, we recently found, have another interesting characterization, that they maximize the distance to product gates. So if you ask, if you're given an unitary operator which is bipartite, what is the distance to the nearest product unitary gate? Turns out that there's a fairly non-trivial problem, has been studied from quantum resource theory for some time, and we derived these results for its lower bound, and also showed that the dual unitaries maximize this distance. So here is a rough picture of unitary operators. It's just a caricature. So dual unitaries kind of lie, there's no boundary really for the space of unitaries, but they lie as far away as possible from local unitary operators. This is a picture of the distance to the nearest unitaries, and you can see here the dual unitary line. They maximize this distance to this for the case of qubits. Okay, so in fact, let me probably also skip this. You can actually construct absolutely maximally entangled states out of these two unitary operators, but it was an open problem for Q equals 6, and using some of the techniques which I alluded to now, you can construct that, and you can see this paper 36 entangled officers of Euler as a kind of a subtopic of how to construct these absolutely maximally entangled states out of two unitary operators. But coming back to circuits, I want to quickly show their relevance for constructing Bernoulli kind of systems. So we take the same brick wall circuits in which we are looking at correlation functions between operators localized at y and x. And then we evolve one of these operators localized at y for a time t, and then look at its overlap with x. And so these are the kind of correlation functions which are easy to study for the case of dual unitary circuits. So what was shown by Bertini, Koch, and Prosen in that first paper which I showed you was that this vanishes everywhere except on the light cone. That is, the only correlations that survive are for x equals y, or so y equals t as well. So x equals 0 and y equals t. So these are the correlation functions that actually survive, and these can be calculated quite remarkably based only on these two particle unitary operators. And this m plus is a map which is related to the two-particle unitary operators U. So they are actually completely positive trace-preserving maps, which are just based on bipartite unitaries U constructing the circuits. And here is an explicit expression of these maps. This is from this paper, Physical Review Research 21. And you can see that it's constructed out of the partial transpose and the realignment operation. So it's a very explicit term for that. Now, do I have how much time? 8 minutes. So what governs the correlation functions in these circuits are in fact the eigenvalues of the CPTP maps, which are constructed out of this 2-qubit or 2-qubit in general unitary operators such as this. So we are really interested in the spectrum of these operators as a function of these unitary operators. And if these eigenvalues are denoted by lambda j, you can ignore the minus. It just refers to another single particle, placing it on another leg of the possible single particle space. So there are really two of them, but you can just look at one of the sets, say lambda plus. So all of these eigenvalues, and there are q square of them, are important, and all of them lie inside the unit circle. This is they can be complex and they lie inside the unit circle. And there is one of them at least, which is exactly equals 1. It corresponds to an identity operator or a trivial eigenvalue. So the other eigenvalues determine the decay of these correlation functions. And explicitly, it's just given by this. Okay, so we are interested in knowing if these lambda j's are leading to a decay in the correlations, and therefore there was some partial ergodic classification of dual circuits. If all the eigenvalues are equal to 1, then the correlations remain constant in all modes and the system is non-interacting. So this happens when the unitary operator U is a swap gate or any local equivalent of the swap gate. It's non-ergodic, interacting and non-integrable. If there are k non-trivial eigenvalues which are equal to 1, then the correlations in these k modes remain constant and it's not ergodic. By ergodic, one would mean that one would at least require that the average, infinite time average of the correlation functions vanishes. And that will not happen in this case. So it's ergodic and non-mixing if there is at least one of these eigenvalues with a which is not equal to 1, but its modulus is 1. So it lies on the unit circle, in which case its average will vanish, so it's ergodic, but it's not mixing because it won't decay. Its modulus is equal to 1. So it will just oscillate about 0, for instance. So ergodic and mixing are the cases when all the eigenvalues, non-trivial eigenvalues, are strictly less than 1. The correlations decay exponentially. And here is the case which is true only if you have not qubits, where you have Bernoulli circuits, where at least, in fact, all the non-trivial eigenvalues are strictly 0. And then the correlations decay instantly. And so, in fact, that this is possible was pointed out in this paper because we have operators which have both partial transpose and realignment equals being unitary. And this is what happens if the partial transpose is unitary. So in terms of circuits or in terms of pictures, those are the pictures. And therefore, since this circuit, or I mean the channel is given by this circuit, we can see quite easily that that it becomes what's called a totally depolarizing channel. That is, it eats up any single particle operator and returns identity. So it's maximally mixed state. So it's a totally depolarizing channel if and only if the U is also such that its partial transpose is unitary. But that's exactly the definition of a two-unitary operator, and therefore perfect tensors. And therefore, if you construct a circuit out of two unitary operators, then the resulting circuit will be satisfying conditions like a Bernoulli system. All the correlation functions will all the single particle correlation functions will instantly decay. So on the light cone, it does not even spread exponentially, it just dies out. But what is also very interesting is that there is very little known beyond single particle observables. For instance, two particle observables, it's not known even in general dual unitary circuits, to the best of my knowledge, that how it is decaying. But in the case of Bernoulli circuits, it's possible to show that two particle observables also decorrelate instantly, just based on the fact that partial transpose as well as realignment is unitary. However, we can't go beyond two particle observables with this particular approach. So it does seem to be a highly mixing and ergodic system. So here is a rough phase diagram for this. And it's interesting that I talked about the entangling power. So what actually is the order parameter in this, let's say what is actually controlling the mixing in these circuits is actually the entangling power, as I will argue here, saying that this is entangling power of a circuit, and this is swap here for qubits, and this is C naught, for example, which has an entangling power of 2/3. In between, if you have any entangling power, it's possible to find local unitaries such that the circuit is mixing. That is, all the eigenvalues are non-trivial eigenvalues of the map are less than 1. However, if you have greater than qubits, let's say q trits and above, there is this entangling power which depends only on the local dimension. If your entangling power of the gates is larger than that, irrespective of what local operations you may have, that is local fields you may have, it will always be mixing. So there is some kind of a transition here. And especially if it's equal to 1, it's guaranteed to be Bernoulli. So there are results in this paper about the largest eigenvalue, the non-trivial eigenvalue. And the maximum mixing rate is defined as a maximum over all possible single particle gates for this unitary operator U. The average mixing rate is defined as an average over all these things, or all the single particle unitaries. And we have some exact results. For example, for qubits, we derive that the maximum mixing rate is given as a simple function of the entangling power of this two particle unitary operator U. And the average is equal to 1 when this entangling power is maximum. And there are results about the average of the largest decay rate or the largest eigenvalue, and it's related to the entangling power of these fundamental gates. Again, you can see that EP equals 1, which is the Bernoulli, is very special. It leads to a 0 eigenvalue or maximal mixing rate. So I think I will stop with that and summarize this. Bernoulli circuits constructed from two unitary operators are possible candidates as an apex of an ergodic quantum hierarchy. Entangling power of two particle building blocks construct the hierarchy, and for some entangling power greater than a kind of a critical entangling power, the circuit is definitely mixing, and if this is equal to 1, it's Bernoulli. There are many open questions. I just put down 2 of them. Like finite circuits for times, or circuits for times greater than L or L by 2, and physical models for Bernoulli circuits. So thoughts are welcome. Thank you.
Thanks, Arul, for a very interesting talk. And we have questions from the audience. Actually, we have a question from Glenn. No? I have a question. So it seems like this duality transformation, the condition which it applies is quite general. So do you think we can probably do some random noise in the time direction, and probably x direction is like a translation invariance, so that it represents some flow case system? Duality is we have a potential, periodic potential, or
yeah, I mean, actually, it was first observed in an Ising model, so it's not that. I mean, in a Floquet Ising model.
Okay, I see.
So it's possible to realize that, if that's what your question.
Yeah. So my question is, what is really condition that this duality applies? I think
what is the condition then?
Yeah. Sorry? What is the limitation of this duality transformation? when it starts to break down, because it.
When does it? Well, no. I mean, so you can have something which is near dual. So it's like constructing maximally entangled unitary operators. So you can have near maximal entangled operators for instance.
Okay.
Then they are not. I mean, typical operators are not dual. Typical unitary operators are not dual. They are fine-tuned.
Okay.
Constructions.
Okay, I see. We have a question from Professor Jae-dong. Yeah.
Okay. So this unitary operator is the time evolution operator for a given time interval. So I'd like to ask, what is the condition for the duality in terms of the Hamiltonian, not on the unitary operator itself?
Yeah, it's a good question. Because this is a finite time evolution operator. So what are the conditions on the Hamiltonian? I actually don't know that. I don't know a good answer to that question.
Still, you have two.
Let me just say that in the case of qubits, it's fairly clear because it's basically the I don't know if I can go back quickly to that. It's just a particular XXZ Hamiltonian. Yeah.
XXG. Yeah. Okay. Then in the dual space, it looks similar?
Yeah, actually, in this case, the dual is equal to itself.
Okay.
Especially, I mean, if you don't have any of these local unitary operators, so these are called self-dual. So its dual is exactly itself.
Okay, thank you very much.
We have a question from Alexei.
Yeah. So what is the role of geometry? Say if I go from one dimension to 2 or 3 dimensions, how would this generalize?
It's a good question. I think there's only limited work in, for example, 2D. But yeah, there are some works, but it's not so easy to, again, generalize as far as...
yes, because I suspect now, I mean, you will have one-time direction, 2 special directions, and you have at least 2 choices how you can...
Yeah, exactly.
Okay, thanks.
If there is there any more question? If there is no, then we again thank Arul for a very interesting talk.
Thank you very much.